All right, so we are going to do the 6.4 notes. And on these notes, our goal for today is to graph a polynomial function. When we graph our polynomial function, we are going to locate its zeros. Its relative minima and maxima. So the first, or the one and only example we're going to do today, is negative x to the fourth plus x to the third plus 3x squared plus 2x. Now the first thing that we're going to do is make sure it's in standard form, because when we go to sketch it, we want to make sure that it's in standard form. Now sketching it is from 6.3, so we need to look at what our leading coefficient is, which here it's -1. Okay, so the leading coefficient is -1. That tells you that the right side is going to go down. The degree is 4. That means that it's even. The left side has to match. Okay, so this is overall what our graph should look like. Now when we go to graph it, all we're going to need is a scientific calculator. If you have a graphing calculator, that's totally fine. We're not going to use the graphing calculator function for right now. We are just going to use the scientific calculator part. So negative, the x value I'm going to plug in first is -3 to the power of 4 plus, I'm going to plug in -3 to the power of 3 plus 3, plug in x, which is -3. This one squared plus 2 times our x is -3. Now I'm going to go through before I hit enter and just verify that this is correct. I have a negative x to the fourth plus x to the third plus 3x squared plus 2x. I made sure all my x's are -3, -3, -3, and -3. Yep, all my x's are -3, and I have -3. I have parentheses around every single -3. Okay, which is very important here, because if you don't put parentheses there, -3 squared is different if it's in parentheses or not. So that answer there is -87. So I'm going to fill it in here on my table. Now, if you have a regular scientific calculator, just hit the up arrow. Some graphing calculators, you have to hit second enter, and it will come up again. And what we can do is now we can change all these -3s to -2 second insert, because it'll rewrite it, 0.5. So I'm going to change all these to -2 second insert, 0.5, -2 second insert, 0.5, -2.5, and this next one is -40.9375. I'm just going to write it all. Some people like to, at that point, since they already have that many digits, they'll go through and they'll change these to -1.5, and they'll skip the -2 for right now so they don't have to reinsert it. So we've done all those, -4.6875. So go ahead, hit pause, and find all the 0.5 ones for right now. And you can write these as 0.5 so you don't have to get rid of digits. So I'm going to pause the video. I'm going to keep filling mine out, then we'll check what you got. Okay, so I went through and I filled in all of those ones. Now I'm going to go back and I'm going to fill in the rest of them. So second enter, I'm going to fill in the -2, get rid of those extra digits. -2, get rid of the extra digits. And you could retype this that many times if you really wanted to. I like to reuse what I already typed in. So I'll make sure I have -2 on all those, hit enter. So this one's -16. Second enter, I'm going to change -2s to -1s. negative 1. And I'm going to keep going on there. So go ahead and pause and find all the rest of them. Okay, so now that you have your entire table filled out, we can go on to actually graphing it. Now, I probably won't graph the extreme situation. So like 87, not going to graph there. The negative 21 and the negative 40, probably will avoid that. But if I can get everything else on there, that's the important part, okay? Because I can see here what's happening is that I have 8 close to 0 to negative 21. It's decreasing. It's getting really far down there. So as you move to the right, coming up on those x values, it's decreasing more and more. You're going in this direction to the left, you're at negative 1, you're at negative 4.6, you're at negative 16, you drop to negative 40, you drop to negative 87. So it's falling really quickly. So if you have to like get rid of some of these extra ones here at the end, but as long as you're seeing that pattern, then you're fine to do so, okay? We just want to make sure we have a good, accurate representation of the graph through here. So I am going to start with my axes. Since I'm going from negative 1.5 to 2.5, I can kind of put it off to this side a little bit. And then I'm going, the highest number that I see, I think, is that 8.06. So as long as I can get to 8. So let's have this be 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So I'm going to put my x-axis right here, and then I'll just see what fits. But I'll at least be able to draw it going down in those directions. So I'm going to put my axes on here. I'm going to put some scales on here. Now, remember, your x and y scales can differ. So I'm going to go up by 1s on my y-axis. 1, 2, 3, 4, 5, 6, 7, 8, negative 2, negative 4, negative 6, negative 8. Now, whatever you do as a scale up here has to be the same down here. Okay, your y has to have one continuous scale. Now your x scale, though, you can change it from what you did with the y. So what I'm going to do is, because I have halves labeled, I'm going to have this be 1, this be 2, this be 3. And then that way I can label a half 1, 1.5 2, 2.5 3, and label as much as I can. So now I'm going to go through, I'm actually going to plot these points. Now, negative 2, negative 16, I know it's way off the graph. So I'm going to start at the negative 1.5, which is at negative 4.6. So a little bit closer to the negative 5. Negative 1 is at negative 1. That one's right there. Negative 0.5 is at negative 0.4. So right about there. And you're just going to continue plotting those points right there. So I'm going to hit pause. You continue plotting all the points that are there and see if you can match mine. So here I have all my points plotted. Now I'm going to go through and I am going to very loosely connect them, but loosely I mean you want to make it a nice curve. So sometimes I even start like kind of in the middle and kind of just make it. So I know this one, I know by the time it gets to negative 2 it has to be off the graph. So I'm just going to be heading straight down there. Okay, just very fluidly, I guess, would be a better way to describe it. You want to go through all the points that are on here, very just curvy. By the time, so I put 2.5 on there, by the time I get to 3, it's again off the graph. So I want to make sure that when I connect this off the graph, I can't pass that 3 mark because 3 is way down here off the graph. So I need to make sure I go off the graph before I hit that 3. Otherwise, if you graphed it like this, you're telling me that 3 is at negative 3, and that's not correct. So you need to make sure that you actually connect this and go off the graph before you get to that 3. So this is what the graph generally looks like. And then we have to locate the zeros. So remember, the zeros are, you can see them based on your x-intercepts, but that's not how we write them. We don't write them as an x-intercept. A 0 is written as x equals a number. So that's how we did it back in Unit 5. So either x equals 0, that's one of the options, or x, it's not at 2.5, but it's not quite at 3, so x is between, you're going to tell me what two values it's between. X is between 2.5 and 3. So you have two zeros, two real zeros here, and those are the two locations. One of them is at 0, and the other is between 2.5 and 3. Okay? So then it says a located relative minimum or maximum. Now this graph has a maximum. Okay, so it's somewhere up in here is your maximum. And relative means that it doesn't necessarily have to be the overall maximum. However, this one does have a maximum. So we actually call this the actual maximum. And this actual max, it's somewhere close to, so approximately that 1.5, 8.0625. That's the most accurate point we have on this. So somewhere around there is where our actual overall maximum is. Okay. Now what a local maximum would be is, let me sketch this down here. If you had something that looked like this, this would be only a local minimum because it's not an overall minimum considering all these points over here go below it. And we'll define that later on, but I just wanted to show you how this one has an actual maximum. Okay. So when we go to state our domain and our range, our domain, remember we did this with the sketch. So we used the sketch before to do our domain and our range. Our domain, our range. Your domain are your x values. So you move to both the left and the right. On your x part of your table here, you could keep going. You could plug in 4, 5, 6, 10, 20, 100, 150. You could keep going. You could plug in any of those values. Our graph goes to the left and it goes to the right. It goes forever in those directions. So because of that, your domain is x is an element of all real numbers. Now your range, though, does not go both up and down. Okay? So your range here has a maximum. So before we wrote it as y, or f of x, is less than or equal to, we just wrote maximum before, right? We just wrote max, and we didn't worry about what that maximum was. We're not going to leave it a maximum now because you can actually see approximately where that maximum is at. What was the maximum value for your y? And it was at that 8.06 number. So all the numbers for your range are below that 8.0625 number. And that's approximate. We're just getting that based on our graph, what we can see, but it's somewhere close to that. Okay, so that's how we would write those. The location principle. It says if the value of f of x changes sign. So let's look at what that means. In our table, we went from having negative signs to 0, or a positive sign. So if you go from a positive to a negative, or a negative from a positive, from one value of x to another, there is a 0 between the two x values. So on our y values, if we go from negatives to positives, obviously there has to pass through 0 in there. So x equals 0. Here you were at positives, then you went from a negative. So the 0 was in between, x is between 2.5 and 3. And then this was your other one. So x is equal to 0, or x is between 2.5 and 3. So that's what the location principle is stating, how you can see a 0 based on the table, which we practiced that back in Unit 5. So that shouldn't look too new to you. That should be a reminder. Okay. Your relative minima versus relative maxima. So relative is like a local. That's the other word instead of relative. It's also called a local minimum or maximum. So we're going to draw this diagram that we did over here. We'll draw that for our definition. So if we had an odd degree function here where we have, obviously there's not a maximum because it keeps going up forever. There's not a minimum because it keeps going down forever. You can also have these in even degrees. They just will look a little bit different. Anyways, this would be A, this would be B. Okay. A is going to be a local minimum or a relative minima. So this would be point A. And the relative maximum will be point B. It is not the maximum point on the graph, but it's a maximum within the area. It's changing directions. The graph went from increasing to decreasing, creating a local or a maximum in that area. The extrema points or turning points is when the graph changes from increasing to decreasing or vice versa. So these extrema points, these are your relative maximum or minimum points, because it's when the graph changes from increasing to decreasing, or vice versa. So if you're increasing, then you decrease, that would be a turning point or an extrema point, which these relative maximums are a version of those extrema points or turning points. Those are all the notes. When you work on this assignment, okay, you're going to do them. They look exactly like the one on our notes. So I already filled in the X values that you need to fill in. Again, if you have those really outrageously large points, you don't have to worry about graphing them. You really don't want to graph them because you would have zoomed so far out on your graph that you'll miss what you're seeing here in the curves. They'll be minimized. So you want to actually get rid of anything that looks a little outrageous to have to graph. So there are 3 of those, and then there's one story problem for you to attempt as well, where it has a sketch of the graph, and it actually is the same sketch as in 6.3. It just has a little bit different information for you. So if you have any questions, let me know.